Felix Enescu, Consult Blue, again and again. Alex Sisu, ETGO, again, and again the panel Scaling Data Processing Pipeline in Big Data.
Mulțumesc! Trebuie să vă mărturisesc că atunci când am fost invitat la acest panel și am vorbit prima dată cu organizatorii, ne gândeam sau mă așteptam să facem un panel, cum se spune la alte conferințe, de nivel 100 sau poate cel mult 100 și ceva. Se pare însă că în sală este cu totul altă audiență și din ce am văzut, cel puțin de la prezentarea de la Big Step, un număr foarte mare de mâini ridicate la întrebări din alea cu vă numiți dezvoltator, știți ce înseamnă X, știți ce înseamnă Y, chestii complicate. Așa încât, acum vreo 2 prezentări în urmă, Alex m-a luat deoparte și a zis, ok, hai să discutăm ce vrem să prezentăm, pentru că îmi pasă mai potrivește cu ce am crezut noi. Și atunci ne-am gândit să mergem către ceva mult mai tehnic, cumva față de tot ce ați văzut de la colegii lui. Este ok, ține de modul în care au ei produsul făcut. Hai să încercăm să intrăm, să discutăm un pic de cum se pot lua anumite decizii, ce variante există și ne așteptăm să puneți întrebări, să discutați. Evident, va vorbi mai mult Alex. Eu eram, după cum spuneam, prezentatorul pentru sesiunea de nivel 100. Dar ceea ce mi se pare extrem de interesant la ce am văzut la ei și cred că putem discuta foarte mult pe tema asta este modul în care alegem tehnologia potrivită la locul potrivit. În primul moment am zice că ok, în lumea asta nouă, Hadoop, Cassandra și așa mai departe, chestii old-time care au apărut prima dată cu, sincer să fiu, cred că vreo 15 ani. Nu mai au ce căuta. Și mă refer aici, de exemplu, la Nagios. La prima vedere, o tehnologie care e de foarte mult timp și nu are ce face. E un exemplu foarte clar, zic eu, de modul în care alegi tehnologia potrivită la locul potrivit, tocmai pentru a obține rezultatele dorite, fără să iei tehnologie de dragul tehnologiei, să te gândești că e modernă, că asta e frumoasă, asta este strălucitoare și așa mai departe. Hai să trecem un pic în revistă ce ai pregătit tu și după care să revenim în discuție și eventual să luăm întrebări din sală. Te rog.
Okay, cool. So my name is Alex Sisu. I'm team lead at Atijo and I'm part of Big Data Research Group. At Atijo, what I do is, like, me and my team, we are implementing parts of X Patterns, the product that Radu presented earlier on. As part of Big Data Research Group, what we do, we do proof of concepts free of charge for anyone who's having an interesting big data problem or a machine learning problem. So we do them for nothing, free of charge. Okay, so as my colleague Felix told you, so initially this session was supposed to be like a panel session with questions and answers, but I'm not very sure how well this will scale and what will be the dynamic. So what I will do, I will go through like several topics related to the scaling of big data pipelines, because they affect everyone that implements and plays with big data, and we can discuss on top of them. So, but first of all, I'm going to go through them, and after that you can address me question and we can have like a nice conversation about them. Okay. First thing first, when you are working with big data, with distributed computing, you have to know the fundamentals. So you can start up on Wikipedia, you can go there, go and read all the topics related to the distributed computing problems. But before that, I'm really curious, like, how many of you did or wrote a MapReduce job on top of Hadoop? Okay, how many of you did wrote a MapReduce job on top of Spark? Okay, awesome. Okay, how many of you do measure your performance when you are implementing algorithms or scalable algorithms on top of your, okay, that's good. Performance issues, okay, that's good. That's good to know. Okay, so that takes me back to where I started. So you have to know your fundamentals. So I recall that someone started up the first, or I don't know, the noon session with the cap theorem. I should also mention consensus algorithm. So these two should be a first, like 2 topics to know. They are pretty complicated, but the fact that you'll understand them, I don't know, a 3 or 4 hours investment in reading, in taking some time to read these things will bring you great benefit later on when you start playing with Spark or Hadoop or I don't know, any other type of platform. Okay. Now, a common topic is, okay, I have like lots of data, what frameworks do I choose? So usually you have, that depends on your use case. You can have like Spark, Hadoop, Storm, or that's, yeah, of course, when you talk about big data, you can also like specify, you can also mention Elasticsearch, Couchbase, you can mention Cassandra or any other tools, but when you want to write code that will run in a distributed manner, you usually go to these 3 guys: Spark, Hadoop, Storm. And of course, my recommendation is to use Spark because it's easier to set up, it's easier to write code in Scala that will run on top of Spark. Hadoop, it's a little bit heavy. You should use Hadoop only if you want to store your data. HDFS, it's very good for that. Storm was just replaced a few days ago by Heron from the guys from Twitter, so you can have a look at it. As Alex Borde said, so the memory benchmarks matter a lot, and everybody knows that. And actually, not everybody knows that, but you should know that because, for example, right now when you want to store your data, you don't want to. You want to choose a distributed file system that allows you to access your data quickly. And usually the cool thing, the meta file system that stays on top of other file system is Tachyon. Tachyon can stay on top of HDFS, S3, GlusterFS, or simple POSIX file system. So usually when you have like huge amounts of data and you want to, I don't know, scan them, you want to have operations in which you're going to provide, in which you will do like lots of shuffling and so. It's better to have it in memory. That's why it's good to use Tachyon for that. Okay, another challenging topic in scaling big data pipelines is the following: is how well will you partition your cluster resources? So imagine that you will have like 100 machines, but if you have like 100 machines and all you do is, I don't know, only 3 people out of like 100 in your company are running MapReduce jobs, it will not scale well because actually they will take all the they will take all the cluster resources and they will leave nothing for you. And usually you want to experiment. You want to experiment by doing data science, data modeling. You want to I don't know, to have at least 3 or 4 cores in one machine and a few bits of memory on another machine to do some experimentation and so. And for that reason, you can use like what are called resource managers, Yarn or Mesos. Mesos is open source, Yarn is coming from Cloudera. I don't know, we play with Mesos, it scales well, it's easy to use, so it's cool. And you can run like Hadoop and Spark and MapReduce on top of Mesos, so yeah, it works. So give it a look, give it a look, only 1 second, yeah. Give it a try, play with it, download the code, learn how it works, and you'll benefit a lot from it. Okay, another thing, data modeling. So usually when you have, usually you process the data in order to serve it in some way or another. Usually what you have, you have like a suite of web services that are serving your data for business intelligence purposes or for analytic purposes. The thing is, how do you manage this whole stream of incoming data of read and write access patterns? So you have to be very careful. So to partition, so to have in mind the fact that read and write in big data, like they cannot overlap too often. So for example, if you take Hadoop, if you are performing like lots of reads and writes operations on top of it, you're gonna kill the name node. So that's what will happen. Or probably, the number of blocks will skyrocket, and after that you're gonna have like lots of out-of-memory exception in data nodes. So For that reason, you have to be very careful how will you manage your those fluxes of data that are coming to be processed, and the fluxes of and the set of data that you want to provide to be served. That's one thing, the data modeling. Another topic is how easy can you do the modeling. Now, when I'm talking about modeling, I'm not talking about like how do you partition it, like in the, like when you are talking about like in the case of Cassandra or Solar. I'm talking about like, I don't know, doing experimentations on those. How easy is it? So for example, it's very easy to, if you have like 1 terabyte of data on a local machine, assuming that you have like, I don't know, several terabytes of RAM, it's pretty easy to run a decision tree algorithm. But how will you do a random forest on top of a cluster? So that's quite a challenging thing to do. For that, you have like several libraries that can be investigated. On the other hand, if you know the fundamentals, you'll be able to implement this algorithm by yourself using Spark on top of a cluster, and then you'll don't need to go to the frameworks. But in order to do that, you'll have to know the fundamentals very well, and on the other hand, to make use of those resource managers, so everybody can benefit from your cluster resources. Okay, another valuable thing, so data locality. When you are working like with huge amounts of data, don't move the data in the cluster. Don't move the data in the cluster. So just don't move it because it will serve your purposes better. I don't know, from one machine to another. Just bring the code to the data and yeah, make it run okay. Another challenge is the data sources. You have like different data sources. Data streams, S3, SFTP. Like usually the companies that are doing big data, like they have like specialized people that are I don't know, data sources gurus that are very skilled in implementing programs that will extract data from different data sources. But it's usually it's a very costly thing. So that's I have nothing to say. So the only thing that I should mention is that when you are working with big data, the fact that you have like many data sources in a project, that will never sound right. So it can generate like lots of delays, and it will not scale well, your entire development process. Okay. Okay, security. Okay, security. Okay, when you have when you work on HDFS or in any other distributed file system, what happens with your data? So it's being will you need do you need is it very valuable data? In this case, you're going to need to backup it. But do you have also the mechanism for restoring it? Are you aware of that? When you are processing personal healthcare information data, and like, I don't know, for bank accounts or like for healthcare reasons, do you have security policies in your company? So being like having lots of data and usually having like a big cluster in which everybody runs its code, it's pretty easy to take the data away from the cluster and to sell it further on. So that's why it's okay for example for you to have like good security policies in your company, not only related to the code but also to the to have some security policies targeting your employees also. Kerberos. So when we are talking about accessing secured resources in the cluster, like for example folders and files of data, then you're gonna, so the only solution that I know about it, maybe there are more, but it's Kerberos. So Kerberos, it was invented in like 75 or in the 80s at MIT. It's based on a ticketing system, and it's based on security levels and permissions that are called realms. I didn't phrase that okay, but you can check it on Wikipedia. Okay. On the other hand, the resiliency of your big data cluster. So if you are are you able to take out a machine from your cluster and still have resiliency? So will your code still work when a machine goes down? Did anyone encounter this situation? I'm really curious about that. Okay, cool, awesome. Are you able to increase throughput by adding more nodes to the cluster and decrease the latency? That's in the case of microservices. So usually when you want to have like services that will serve data for different purposes, you want to have them stateless services that will just read the data and deliver them further. For that reason, it's if you'll use microservices, that will scale very well. So basically, you will be able to increase the throughput by just adding more resources to the cluster, and that's okay. Failures. Are you able to detect failures? Are you able to recover from failures? For example, do you have a strategy for which, for example, a web service fails? What will happen then? How many of you deployed or are still deploying web applications in Tomcat? I'm curious. Okay, awesome. And what happens like when you are encountering an out-of-memory exception and so? So usually it fails. So yeah. So one challenge is this one, to be able to detect failures and to be able to recover from failures. For that you have Spray or Play framework, so it's cool. So these are the topics that I want to provide for discussion. So if you have any questions. Okay.
Mulțumesc. Uite, avem deja o întrebare.
Hi. So you said before, what do you do with run out of memory? Do you have a solution?
Sorry?
Do you have a solution if you deploy a Tomcat and you have run out of memory?
Yeah, of course. So you'll have to rewrite your web service in Spray, and I don't know, using actors, and that will scale because there will be like self-contained applications. You can put that Spray application in a Docker container, and you can like play with that Docker container. So you can create like many containers that will just scale horizontally, and
So
that will
pretty
be
close to scrap and rewrite.
Sorry?
Pretty close to scrap and rewrite.
Yeah, something like that. So the thing is, so Tomcat is a very good application server, but the thing is that if you have like lots of applications there, each time you're gonna have to deploy something, I don't know, the availability of the other web services that are being deployed along with your application in Tomcat will decrease. So in case of a simple restart, for example, you're gonna lose all your web services. So this will not scale. That's why it's very good to have like separate independent processes for each of your web services. Sorry? Of course you can do that, of course, but I don't see the point of, I don't know, bringing 30 megabytes of data, I don't know, just copying it around in the cluster. It doesn't make sense. So it's much more easy to have like, I don't know, an application copied several times, but not along with the Tomcat itself. So that, yeah.
Until we have another question, I would have a question interesting. You mentioned a couple of times about failures and recovering for failures. How about designing an application specifically for an infrastructure that will fail you? And I'm pointing, for example, we talk a lot about processing vast quantities of data and processing that requires lots and lots of CPU cycles. Let's think, for example, how would you organize or what advice would you give to someone who would like to use, for example, spot instances on Amazon?
So I've never played with them, so I understand that they are cheap and you can use them.
But they can be taken from you.
Yeah, sure. But it depends on your cluster. For example, both Hadoop and Spark, they have like pretty good resilience mechanism. You can use spot instances, so if someone will fail, that task will be automatically reallocated from one instance to another, and you will not lose anything. But usually it's not, it's usually to go, so the best advice that I have is like, I don't know, buy SSDs and bare metal, and then you don't have to worry about your developer skill. But usually it's better to have like a combination of those. So very good developers and also bare metal.
And a lot of money.
Yeah.
That
lots
will
of
help
money.
too.
Yeah, that's true.
I have a use case for Spark instances. Like if you have a queue of data and then you have some lightweight workers and you don't have urgency, right, in processing the data, then you can just sort of have spot instances, and if the price is too high and your spot instances are shut down, you still have queuing the data, and when things are cheap, then you can sort of catch up.
Yeah.
Yeah. That's true. So another thing about failure, for example, regarding the streaming of the data. Usually, what people do when they want to stream data, they are using like an open source queue, Zero Cube, Kafka, or so, and usually what happens is sometimes you're going to lose connectivity on your machine. And a very good use case that I implemented was, I don't know, for that small amount of time when you're losing connectivity in your queue, you're just going to have to stream the data locally. And after that, when you're going to get the connectivity back, you're going to start to you're going to have to resume your streaming to that queue. And that's it. It's quite a fairly simple use case, but that illustrates very well what will happen when I don't know, when you start to process large amounts of data and you don't have connectivity, and you put all your faith in those distributed platforms or distributed queues, or I don't know, any other thing that is being distributed. But usually the file system, I don't know, using the file system as a last resort, it's one of the best alternatives that you might have for resiliency and for recovering from failures.
Okay, interesting idea to use the file system. I suppose you are referred to the really local storage of each individual
Just write everything on the local storage.
Yeah, usually it restarts and your data is still there.
Yeah, exactly.
Those guys writing file system drivers usually they are doing that since, I don't know, 50 years ago, so they are pretty good.
Yeah.
You mentioned a lot about this big data and using specific technologies. When you are thinking of increased throughput by adding more nodes, is this a thing that will be solved automatically of using those frameworks and technology, or it's a thing that is very much up to the individual developer using those frameworks?
I think it's it's both. So usually so when you have to start a new machine, of course you're gonna have to go in, I don't know, in the Big Step interface or Amazon interface, and I don't know, just select a machine and start it. But I don't know, adding a machine to the cluster right now, it's pretty easy. Usually when I said about like increasing throughput by adding more nodes to the cluster, I was referring to the application layer. So to the part where, I don't know, you have like more web services, or for example, where you are helping your Spark or Hadoop infrastructure to process more data in a faster way. Because you're gonna make use of more CPU power, and that will work.
As a personal curiosity, in your experience and also to the room, if we are talking to, let's say, quite CPU intensive jobs, or whatever specific example you guys have, it's more cost effective. Okay, I'm the guy with think more business, so that's why lots of my questions are related to costs. It is more cost effective to buy fewer larger machines from, I don't know, Google or Amazon or Big Step, whatever, or more smaller instances to perform a specific amount of work in a specific amount of time.
Okay, cool. So it's better to have like bigger, larger instances if you don't care about the costs. So usually that will help you avoid the shuffling of the data in a cluster, which is a very expensive operation. And it's better to have everything in one machine in one single RAM, you know, like, yeah. So
it's
it's a trade-off,
yeah.
You know, the money.
If you want to gain time, buy the biggest machine you can afford.
Of course, yeah.
Okay.
Same sort of experience, like buy bigger machines. But sometimes you have trouble. For example, some things are single-threaded, or like if you have Java applications, if you have heaps bigger than 32 gigs or so, you will lose the compressed pointers, so you will actually have more wasted sort of heap space. Can you come up with some examples and sort of how, or someone else in the room, like
so
issues with big machines, like Alex pointed out, like you have machines with CPUs in different sockets, and then you have some latency that's introduced, and you can sort of work around that by using NUMA something, or
yeah. So first of all, I don't know nothing about compressed pointers. However, I can provide a use case in which, I don't know, you might benefit from this, I don't know, huge amount of memory that you might have. So instead of, so for example, assuming that you have on a single machine like 96 CPU cores and, I don't know, several terabytes of RAM, it's pretty easy, for example, to implement some sort of distributed random forest. Or for example, you can implement like lots of hyperparameter optimization methods for, I don't know, whatever kind of algorithms do you have in mind. Otherwise, you're going to have to distribute the workload, to shuffle the data in the cluster. I don't know, split the workload on each machine, and after that compare everything to bring the data again to you, which is very costly, And it's easier, for example, to have it in one single machine. But that's more, my answer refers to like some specific algorithms that benefit a lot from having like lots of CPUs and lots of memory. But I'm not very sure like if I provided a very good example for a typical application or so, for a normal use case.
Actually, that is very insightful. Like you can have multiple small nodes on a big machine, and then
yeah.
sort of avoid working through the network, and it's
Yeah.
You're still better off.
Yeah, exactly. You're welcome.
In a sense, participating to this panel kind of makes me sad. In a sense that I was under the impression, at least until now, that we live in a moment where everybody can process almost any amount of data at once just by rent. Okay, some machines, some small machines from Amazon, Google, whatever. Rent 100 machines for one day, and they can process everything and so on and so forth. And I'm here, and I'm hearing you from you guys, the expert, that by the way, you should buy the bigger machine you can afford. So that's not really a good thing to. Yeah. So what do you think?
Yeah, I'm all for like, I don't know, big machines and costly machines with lots of CPUs and SSDs and huge amounts of RAM. So if you can afford them, it's very good, and it will gonna save you time. So it's much more easier. For example, it was still 2 years ago when Hadoop was still having problem with lease exceptions. So that meant, like, for example, if concurrent reads on some sort of a block, you are bottlenecking or you are choking the name node, and he wasn't able to provide no type of access to that block of data in Hadoop. And it was like 2 or 3 years ago. So this distributed file system, usually they don't, usually they are meta file system on top of normal file systems. And on top of this HDFS, you have, like, for example, another distributed file system, which is called Tachyon. And you have like this sort of meta distributed file systems. But if it would be for me, imagine that all these problems can be easily solved if you have, like, I don't know, a huge amount of storage, plain SSD storage, store all your files as text, or I don't know, using a specific or a very powerful compression algorithm or so, and just, I don't know, process them in a parallel way using all your cores. And if you have all of that in one single machine, of course, your performance will skyrocket instead of using a cluster of machines.
So what I understand from here, with my limited, I admit, obviously, experience in this area, is that practically lots of the algorithms currently used for regular processing in this regularly called big data area are actually algorithms that not scale very well, that are not very parallel in nature or in design. Because I'm hearing a lot about choke points, virtual on virtual on virtual, and contention and blocking and so on and so forth, versus algorithms that are totally and inherently parallel, like, I don't know, processing 1 million pictures to create panoramas or things like that, which is clearly parallel and nothing has to be communicated and whatever. Anybody here can answer? It's a very theoretical question. If anybody reads the publication in this area, maybe are we expecting any new advances in this area? Better algorithms, more parallel algorithms, anything around that?
Not necessarily, because now you can use HDFS over raw devices, and now it's custom behavior for big data center to use GPUs, general purposing units, from Atmel, from different providers, Texas Instruments as an example. You can use them. I don't know if you have the chance to play with the Java distribution for the ARM processors.
I play with Theano, which is a Python port on top of like C bindings that allow you to code on GPU, and usually,
and
so
they
and
actually
Torch
can
also
have performance in terms of implementing algorithms. So all that part of adapting data, rounding data,
all of it,
data you have over there, and you can reduce a bit of power on that area.
Yeah, and then they're on the GPUs, but somehow on GPUs you have the same problem, the same data shuffling problems that you have like on a normal clusters. Not quite the same, but pretty much the same in the sense that then first of all you're gonna have to write a very optimized code in order to have your code running on the GPU. Second, you're going to lose time each time you're going to transfer data from the memory to the GPU itself and bringing it back. That's why it's better to have like huge, very well optimized pipelines for GPU. I don't know, for your code that runs GPU. I'm not very sure. So the thing is that, for example, if I'm performing multiple matrix multiplications and so, and if I want to multiply a matrix with itself, a square matrix with itself for 10 times, and after 5 times I'm checking the result, I'm going to stop the pipeline because it will just not. So what I will have to do, I will just stop the process, get the data from the GPU, present it on my screen, and return to the process. I'm not very sure if this example was pretty clear.
Can interfere with
what I want to underline is the fact that if you want to bring the data from your GPU back into your main memory, you want to display it on your screen or so, you're going to lose time. And that's why it's better to have to use frameworks like Theano that will provide all these optimizations for you. So they will optimize at maximum the code. You're going to have like huge flows of code that will, that will get translated in some really smart C code, and that will get executed on GPU. Also, I have an example related to that. Are you curious to see it? It's related to neural networks implemented in Theano. Okay. For example, here I'm training a neural network to recognize the MNIST. I don't know, the character images from the MNIST dataset. The thing is, I just want to show you like how easy it is to code in Theano the whole backpropagation algorithm. The thing is, Theano, it's a Python library that is building, that it's making use of C bindings in order to run on GPU. This doesn't run on GPU, it just runs on the current machine. But if I will have to run it on a GPU machine on EC2, that will go like that, you know, like it will just snap. And what I want to share you, the whole training algorithm takes here. So here I'm specifying the fact that I'm multiplying some matrices, and at the end I'm performing like a gradient descent on the matrix, and here it. And here I'm performing the gradient. Now, if it would be for me to compute the gradient for each weight in the neural network, it will take me like a lot amount of time and code to have it. But on the other hand, I have Theano, which allows me to do symbolic differentiation, and it optimizes the code that I will have to run for on the top of GPU. And yeah, and this code that you see there running, so that runs usually like in a snap in on a GPU instance. Okay, time's up. I see that. Okay. Cool.
I would like to end with one last question to the audience. We hear today, at least in this room, and in this stage, a lot of very interesting stuff, very juicy and cool things. Please raise hands, all of you which on a not daily basis, but in general, did something related to these things at work. I mean, and not just regular, I don't know, regular web application or regular, really. Like
Big up,
30?
respect.
Yeah.
Awesome.
Yeah. You are self-selected, but still a very, very respectable percentages.
Yeah.
Okay. Alex?
Okay, cool. Thank you very much then.
Thank
Thank
you.
you, Felix.